I'm building a weather station as an IoT project based on the Raspberry Pi Pico W, and in this video I'm going to talk about the PCB design and how I'm interfacing about a dozen different sensors into the Pico W. These need to meet my sensory collection strategy and my power management requirement. Yes, the project's going to be battery and solar powered, which has added quite a lot of complexity. Let me tell you all about it. Hi, I'm John, your concierge to the world of the Raspberry Pi Pico, Pico 2, robotics, IoT and other fun tech. Remember to subscribe and join the community. I'm not an expert at PCB design, I have to admit that. My background's more in software and architecture, but I can turn my hand to PCB design though and share some of my experience. This project has quite a lot of interfacing into the Pico W. In fact, I've used just about every GPIO pad available on the Pico W. Some of that's for the core requirements to interface the sensors, some additional features that I may not implement, such as a backup storage to an SD card, and some future-proofing for other potential uses. The problem with lots of connections is that when you're working with this on a breadboard and trying to validate your hardware, which is the step I go through, you start chasing bad connection joints as much as validating design issues. That's the point where you jump to a fabricated board. And for this board, I might have done that just slightly too early, as there are a few additional features which are not performing quite correctly. I probably need to go through one more revision of the PCB design, but the core features work, and that's what I'm going to talk about today. If you like this video and it helps your learning or projects, why not drop me a cash tip using the super thanks button below the video. I'm saving these up to get myself to open source in San Francisco with the other makers next year, and I appreciate your help in getting me there. And I'd love to see you there too. Please hit the like button on the video and subscribe for more. This project is largely about integrating sensors onto my Pico W so that I can actually sense all this weather data, and then doing some management of power so that I can survive on solar and battery. So of course we've got our base components of the rain, wind sensors, speed and direction. Then I'm going to do temperature and humidity via an AHT10. Then I want to actually sense some data also around the battery. So how is the battery going? Where are we charging it at the moment? Or are we actually running on battery power? So I've got all of that data coming through. And then I'm going to use that DF Robot Sen 0500 that I've looked at previously, which I'm going to use the atmospheric pressure from UV and ambient light. And I can use that to sort of understand how am I getting light onto the sensors, onto my solar panel, how are things going like that. Temperature and humidity on this sensor probably aren't going to be terribly useful to me because it's going to be in a glass jar so that it actually can get light to it, which I think is going to cause issues for the temperature and humidity. So the design for this I'm doing in KiCad, which is my preferred design software for doing PCB layouts and one that other people have recommended to me. So I use that to do the schematic and then go from the schematic to a PCB layout. And this is a 4-layer PCB that I've produced for this one. And then I can then get that fabricated by a quality fabricator like my friends at PCBWay. And then I can add all of the components onto the top of that so that we've actually got a populated board and we can go and do the rest of the project. This video is sponsored by PCBWay. PCBWay have more than sponsored this video. They've also helped me with the fabrication, taking my design from KiCad and validating that it can be successfully fabricated, then producing a great board for me and shipping it to me, all within about a week. PCBWay make the whole process easy, from selecting the type of the board, this was 4 layers and 1.6mm thick, to the colour and fabrication options to be used in the fabrication process. They keep you informed of progress and track the board right to my study, where I can open it and begin the assembly process. You need a partner like PCBWay too. So wind and rain, well, that feels like the description of the UK weather right now, but those are really the sensors that I guess are at core of this work. So let's have a look at how we're going to read from them. So the rainfall sensor first. Well, the rainfall sensor that is in this kit is actually a read sensor. So basically the read sensor triggers every time 0.2794 millimeters of rainfall drops. And so I will get a signal every time that happens. So what I'm going to basically do is use that as a pull to ground switch going into a GPIO port. Now this does bounce a bit, this switch, and if I was reading this through an interrupt mechanism in software, I could handle that, and I would handle that in software, and that would be my normal way of doing it. But I actually want to do a trick with this when we get to software, so I'm actually going to be counting it via the PWM module on the PicoW, so that I don't actually have to have the core active in the counting process, and it can count why the core is actually asleep. So to do that, I'm going to have to tame this a little bit, and so there's going to be a 0.1 microfarad capacitor across that, just to smooth that out enough that actually we're not getting issues. Now the rainfall sensor, like both of the sensors on this, comes with RJ11 6-pin connectors. Be careful, RJ11s often come as 4 pins, but they've used 6 pins on this, and so finding 6-pin sockets has been one of my little problems with trying to build this PCB out. We can therefore design in on my schematic basically a rainfall connector, which is just an RJ11 6-pin connector, and it's got that capacitor across between the two connections. Now the documentation for this didn't really tell you which pins to use, so this was a little bit of a trial and error. How about the wind speed? Well, that's very similar. It's still a read switch, and again this time it's about rotation. 1 rotation per second, or 1 signal per second, is equal to a 2.7 kilometers per hour wind speed. Sorry, I'm going to go very metric in my measurements, which isn't always true in weather, I know, but that's what I'm going to talk about here. So that's what we're measuring. So again, we can go with the same strategy, just use a capacitor across there, 0.1 microfarads, to just tame that, and I will again use PWM to be able to count, and then do checks against time to see how many counts per second we are getting. The wind direction is a little bit different. It's still actually read switches, but now it's a whole cluster of resistors, and the way it's designed is 1 or 2 resistors can be active at any one time based on the position of the magnet, and that gives you this table of resistor values that you might get and what the angle of wind is for that position. Presumably you set it up accurately, but you know, we can adjust the angle anyway and adjust things in software, I guess, which is what I will do. So to measure this, what I'm actually going to use is a voltage divider, because to get those resistance values is to something that I can get a sensible value on the Pico, I really did need to put a voltage divider in, and so we use a voltage divider between ground and 3.3 volts, where one of those resistors, R1, is going to be the input coming in, and that resistor bank that's actually on the wind direction sensor or weather vane, and the other one is going to be a resistor that I'm going to add in place. And that resistor that I'm adding is 4.65 kilo ohms of resistance, which seemed to give me the right sort of voltage range to be able to actually tell and easily work out what the direction. The other problem with this potentially is if we actually connect this as a voltage divider between ground and 3.3 volts, then I'm drawing current all the time through this, and burning current may not be a huge amount because these are quite large resistors, so we're not going to get a huge wattage drop across them, but we are going to get some power drop across them, and I don't really want to drop any power that I can possibly avoid. So I'm going to put my Pico to sleep all the time, so I'm only actually going to check the wind direction every 2 minutes or so. So why would I actually want to be burning current when actually I'm not checking what that value of that voltage is, and therefore that resistance and direction? I wouldn't. And to avoid that, what I'm actually going to do is put the source into this voltage divider. It's actually going to come from a GPIO pad, And so I can pull that GPIO pad high in order to actually do the measurement and actually do the voltage divider on there, and then drop it back low again and while I go to sleep. So the connectors coming out of the RJ11 connector here are going to go basically between our wind anemometer is just that read switch, and we've got that capacitor on there, and that's going to go off to a GPIO pad. And then we've got wind WAP, which is the power coming in, and I'm going to raise when I'm actually doing the sensing of directions, and the wind VAD, which is actually the analog to digital converter input. So I'm connecting these round. So most of these things are GPIO 13 to 15, which has got the anemometer and the rain sensor plus the power for that direction sensing of the wind, the weather vane. And then the analog to digital converter is of course going into one of the ADC pins on the Pico, and I put that into GPIO 28 or ADC2. For temperature and humidity, I'm going to use an AHT10. Now I've looked at the AHT10 before, and I'm going to use it as a module in this case. One of the reasons I'm going to use it as a module is I need it to actually be away from the rest of the PCB, so it's not affected by any heat or anything coming off of the Pico. So it's going to be somewhere in the middle of my Stevenson screen. Now an AHT10 is just an I2C device, so I can just connect that up onto the I2C bus, and that's all nice and easy. Well, that's absolutely true. There's just one thing about that is temperature and humidity are slow moving sensing data. So I don't actually need this data all the time, and I don't need this sensor therefore to be on all the time. So it's my intention to actually turn this off and just sample it every few minutes and use that then as my data source. So to turn this on and off, I'm going to use a 2N7000, which is an N-channel MOSFET device. And use that basically as a switch, and that way I can put a control in, signal in to turn that on and off, and when it's on I will be able to drain the ground from my device through the MOSFET to complete the circuit for power for the device. So that means then when we're connecting this up to my Pico, I'm worried about SDA1 and SCL1, which are going to be my data lines coming for I2C, then VCC, which is going to be the 3.3 volts, and then a special ground, which is going to be the one that is going through that 2N7000 in order to switch things on and off. And I'm going to patch those all through to the Pico W. I'm going to add to the AHT10 with some data from the DF Robot Sen 0500. So I'm really interested in the atmospheric pressure here, UV light and ambient light levels. The temperature and humidity on this I think are going to be affected because I'm going to end up putting this in a bit of a glass jar at the top of the unit so that I can really focus on those light readings, in which case temperature is going to skew based on the amount of UV hitting the jar. This device has both UART and I2C interfaces, but for this project I'm just using the I2C, which is what I used on my previous video on this. So again, it's going to be on the same SDA1 or I2C1 bus into the Pico W. So we're interested in SDA1, SCL1, and of course power. I'm going to again turn this off. This is more important to turn off really than the AHT10 because this actually draws quite a bit of current. It's about 30 milliamps of draw through here, so I want to turn this off and make sure that this is only on when I'm actually using it, though it has a bit of a startup time of about 10 seconds, so you have to be careful that you're giving it enough time to initialize before we start getting readings out of it. And of course patch through to the Pico in the same way. My power source outside is going to be battery and solar. Well, that's the plan. And I'm going to use the Pimeroni LiPo shim in order to actually connect in the battery. These really need to be treated, from my point of view, as sensors and data sources too, because I want to know how this is working out and how much time we're getting on charge, what the battery level is, and adjust some of the parameters of this to make the project successful. And I've previously looked at measuring battery usage and how you can do that on a Raspberry Pi Pico W in particular. Here really we are going to just use the inbuilt capability, because between VBus having the solar input, which is going to come through from basically the USB port, and battery, which is on VSys, we've got all of the data I really need. I have added a real-time clock, a DS3231, in the shape of a ChronoDot version 2 onto the board, and to use that to potentially wake the microcontroller from sleep mode. Now, I don't really need that. I could probably be using the onboard real-time clock to wake it, because I'm going to go into deep sleep rather than dormant, so that I can use the PWM functions to be able to continuously measure the readings coming from wind speed and indeed rainfall. The ChronoDot version 2 and the DS3231, it's another I2C device. So it's going to be on the other I2C bus for my Pico. I'm going to put it on I2C 0. So I'm patching through SCL 0 and SDA1 to this. I also need an interrupt driver coming out of this, going to a GPIO port to tell the Pico to wake back up again. And there's an opportunity for me to constantly measure the battery on my real-time clock to see how that battery is decaying and whether that battery is maintained or not. So we'd take the battery port into one of my ADCs as well. From a power point of view, I've sort of designed in two strategies here, and I've put in a little bit of a jumper. So I could easily jump this so that power is directly coming 3.3 volts off of the Pico W's power supply, or I can actually put it on a control and I use a GPIO output from the Pico to actually power the DS3231, and in tests that works fine. This device actually pulls very little current, so that seems to work viably. Options playing around with this. Then I've basically patched this through onto the I2C 0 bus onto the Pico and given myself the real-time clock, battery and interrupt connections through as well. There is a bit of non-sensor work and design work around the board as well. For instance, on power, so I've put in a capacitor across the main power to the unit. The real reason for this is that I was having issues measuring the power draw through my multimeter, because when Wi-Fi kicks in, it actually kicks a little bit too much power for my multimeter to handle. So the capacitor just smoothed that out a little bit. Is this capacitor really required for production use of this board? I don't think so. I want some status data because it's really quite useful to be able to walk up to the unit physically and see what state it's in. Has it connected to Wi-Fi? Is it awake? Is everything okay? Has it detected some sort of error? So I want some ability to do that, and I'm going to do that through an RGB LED. But of course, I don't want that RGB LED on all of the time. So I've designed in here both a switch and as well as the LEDs. So basically, I will only light the LEDs and give myself diagnostic visibility of the LED when that switch is pushed. Now, a hardware engineer probably would have designed that as a hardware circuit that would have done that all in one go. I decided not to bother with that and designed it so that the processor will turn on the LEDs when it wants them on, based on when the switch is on, and I'll do the actual clever bit in software. I'm going to put a reset switch on here. Nothing really very clever on that, just helps me out while I'm testing things and getting stuff up and running. I've also designed in the capability for some non-volatile storage in terms of basically a micro SD card, and putting in a micro SD card module on SPI on there. Now, In test, I'm getting a little bit of an issue with this and a little bit of an interaction, possibly because of the way that I'm powering it and using another MOSFET to allow me to turn it on and off and things. So this isn't working, but it's a potential expansion. Also, my major use case for the micro SD card really is a redo log to be able to hold data that I haven't actually managed to send yet over to my server. So that I can handle through the internal flash of the Pico. So I don't really need the SD card at all. So I'm probably going to drop it from what I'm actually going to release initially as my first version of this. And I've also designed in quite a lot more expansion on I2C0 so that I could run some additional I2C0 devices on there. And there are a couple of connectors for that and the potential for another MOSFET to be able to turn on and off that channel. Now, that's clashing a little bit with what I'm doing with the real-time clock. So again, perhaps I haven't thought that through as much as I should have, but there are some potential expansions off the board that might be useful. Some of these might need further refining in a future version. So I prototyped all this up on a breadboard. It had the SEN 500s on there as well, which I've taken off of there, and some other bits and pieces, which made the board look quite complex and quite hard work to actually maintain all of the connections and find dodgy connections and things. So it did get to a point where I was spending more time finding issues with my breadboard and my ability to push wires in than I was actually debugging my circuit. So I've then moved this to a PCB. And the PCB's been manufactured and by my friends at PCBWay. It's a 4-layer PCB, and I've tried to use some rules with how I'm using those layers. So generally, the top layer is the power layer, and that's got all of the 5-volt or 3.3 volt power connections on. Then the internal two levels, 2 and 3, are basically the data signals, and I've generally gone vertical on layer 2 and horizontal on layer 3, well, more or less to try and just fit those connections in. And finally, ground is on the bottom of the board. Of course, I've over-engineered this by putting a whole load of additional connectivity and capability on there, which is probably going to mean I'm going to actually only partially populate this board in production. Once the board comes back from PCBWay, only about a week for them to do that, I've got a great board to be able to solder up and put all of these components on, and then get into the testing phase of this project to see if we can actually get closer to getting my weather station out there and actually doing some work. The real test of this is whether it's going to work in the field, quite literally as a weather station. I have the software nearly done, except for the power management testing and sharing those power management results with you. Whether I can continuously run this on solar and battery in the UK is the real key here, and it's winter here, so it's going to be interesting. I've designed in lots of sensor data to help me evaluate that, so I'll know when the battery is on charge and how much battery power I have left. And using the DF Robots SEN 0500, I'm even able to record the ambient light levels and UV hitting my solar panel. So I think I have lots of data that will help me assess if this project is going to work. Stay tuned to hear how I get on. If you like this video and it helps your learning or projects, why not drop me a cash tip using that super thanks button below the video. Remember, I'm saving these up to get myself to open source in San Francisco next year, and I'd appreciate your help in getting me there, and I hope to see you there too. Thank you very much for watching. If you enjoyed the video, then please hit the like button and please subscribe to my channel so you don't miss the next video. Bye bye for now.